Hello students, today we will start model number 5 of the CMOS Vlsi design. Okay, so into the Vlsi design, model number 5 is memory, registers and timing consideration, that is the aspects of the system timing. Then last point you will get the testing and verification. Okay, so then in this unit we are going to study about the memories, and in this case memories were different memory cells we are going to study. So into this we are going to study about the 3 transistor dynamic cell, then we are going to study about the 1 transistor dynamic cell, then pseudostatic RAM. Okay, so here we are going to study all these memory elements, that is for different area different performance will be there. So what are the different performance we are going to study in detail into this model. Okay, so before going to that, so we must consider some set of rules regarding the writing and replacement of the memory. Okay, so we have to go for the system timing considerations. Why we go for system timing considerations? That is, so we have to make some standard rules, that is how much timing it should be for reading, writing. Okay, and we require refreshment of the memory. So for that purpose we require system timing considerations. So what are the different system timing considerations? These are as like this. Okay, so two-phase non-overlapping clock is assumed to be available, and this clock will be used throughout the system. So we have to use two phases. Okay, so the clock phases are assumed to be phi 1 and phi 2. These are the two different clock signals, phi 1 and phi 2. Phi 1 is assumed to lead phi 2. Phi 1 is assumed to lead phi 2. Another consideration, that is bits, or that is data bits to be stored are written to register, storage element and subsystem on phi 1 clock cycle. Okay, on phi 1 of the clock cycle. Okay, that is write signal is ANDed with phi 1. What is that? Data will be stored onto the rising edge, or what is the with the clock cycle, that is phi 1 clock cycle. Okay, so hence we can say that is a write signal is ANDed with phi 1. Okay, bits written into the storage element may be assumed to have settled before phi 2 signal. Okay, and the phi 2 signal may be used for refreshing the stored data. Okay, means what? That is bit stored into the memory element, it is stable before doing the refreshment cycle. Okay, so delay through data path, combinational logic, etc. are assumed to be less than the interval between leading edge of phi 1 of the clock and leading edge of the following F2 signal. Okay, so delay through the data paths, combinational logic, etc. are assumed to be less than the interval between phi 1 and phi 2 clock signal, leading edge of the final and phi 1 clock cycle and leading edge of the phi 2 clock signal. Okay, so then next consideration, bits or data may be read from storage elements on the next clock cycle of phi 1. Read signal is ANDed with phi 1. Okay, thus read and write signals are mutually exclusive. Okay, And the last consideration is general requirement for the system stability is that there must be at least one clocked storage element in series with every clocked loop signal path. Okay, so these are the some timing considerations. There are some timing consideration for reading, writing and refreshment of the memory cycle or memory. Okay, so then we'll discuss some commonly used storage elements. Okay, some commonly used storage elements. Out of that, we'll start with the 3 transistor dynamic cell. So the commonly used storage elements. The storage elements are compared on 3 parameters. There are various elements. Okay, that is, as I earlier said, that is, it is a 3 transistor dynamic cell. Then you will get 1 transistor dynamic cell. You will get then you will get the pseudo dynamic cell. Okay, so 4 transistor CMOS cell, 6 transistor CMOS cell. Okay, all these we are going to study, and for so their performance will be studied onto the various parameters. So out of these parameters, 3 are the most important parameters. There are area requirement, estimated dissipation of power, estimated power dissipation per bit stored, and volatility. Okay, so we know that for implementation, silicon area for every cell will be different. Every technique it will have different. Now we will take one example, that is 4 mm by 4 mm memory size will be there, and into that 4 mm by 4 mm memory size, how many number of bits will be stored, that we will find, and according to that we will discuss how many area or which memory cell will have more bit capacity. Okay, and then we are going to discuss about the what will be the power dissipation across through it. So what is the resistance and current, so we will find what will be the power loss across the memory cell. And most important point is that the volatility, data stored onto the gate of the capacitance, it have leakage current and it will discharge that data. Okay, so the data is erased from the memory for up to some time, therefore we require a refreshment cycle. Okay, so what will be the refreshment cycle we require, that we have to study. So depending upon this, we are going to study all the various elements. Now we discuss about the first 3 transistor dynamic cell. We'll discuss about the 3 transistor dynamic cell. So for the 3 transistor dynamic cell, arrangement of the 3 transistor dynamic cell, it is like this. Okay, so this is for NMOS arrangement. This is for NMOS arrangement. So this is depletion type transistor, and the transistor T1, T2 and T3 are used as a one storage elements. Okay, so this 1, 2, 3, 4 transistors are used in a dynamic memory cell, or here it is, actually this will be the active load, this is the load will be there, or resistance part will be there. Hence actually there are 3 transistors, T1, T2 and T3 will take part in the storage element, and hence it is called as a 3 transistor dynamic cell. And in case of CMOS, we can use the same structure. Instead of that depletion type transistor, we are going to use P type transistor. Okay, now we will discuss how to write the memory and how to read the memory. So in case of write operation, so we have to store the data onto the capacitance. Okay, so this is the bus line, whatever the data here, that will be stored onto the gate capacitance of the T2. So for write operation. For write operation, we have to make this write line will be high, so that the transistor T1 will on, and we have to make a read line, it should be low. For write operation, read should be low and write we have to make it high. Okay, so whatever the data onto the bus will be stored onto the gate of the capacitance T2, and after that we have to make again T1 will be off, write we have to make 0, so the data will be stored into the gate capacitance of T2. Now in case of read operation, again we have to read by using make the read line is equal to high. If you make the read line is equal to high, then transistor T3 will be on. Now if data stored will be is equal to 1, okay, if the data will be stored is equal to 1, then it will make the bus will be high, and if the data stored is equal to 0, then it will pull down the bus. Okay, in this way the data will be stored and the read will be in case of this 3 transistor dynamic cell. Okay, so then we are going to compare. So first of all we will see this, and this is the circuit diagram for this NMOS 3 transistor dynamic cell, and if we replace the transistor with the p-type transistor, it will be the CMOS 3 transistor dynamic cell. Then we'll convert this circuit diagram into the stick diagram. So this is the arrangement for the CMOS 3 transistor dynamic cell. This is the p-type transistor, and this p-type transistor will be the above demarcation, and there are 3 transistors. Okay, so this is one transistor, this is another transistor, and this is one more transistor. Okay, so what is the area required for it? So we are going to consider the how much amount of area, how many bits will be stored into it. So area required or memory capacity. So in case of 4 mm by 4 mm silicon chip area, the data stored can be above 4.8 kilobits. Data stored it is less than 4.8 kilobit. Okay, and volatility, that is the cell is a dynamic and it will hold the data only for as long as sufficient charge is remain onto the gate capacitance of the T2. Okay, as the gate capacitance of the T2, when the T1 will be off and T3 will be off, so ideally it will be hold the data, but it will have some leakage current. Okay, this transistor it will have some leakage current, and hence the gate capacitance it will discharge, and hence the data is going to be vanished after some time. Hence we require the replacement. Okay, so this is about the 3 transistor dynamic cell. Then we'll discuss about the 1 transistor dynamic cell. So as we discussed here, in case of this 3 transistor dynamic cell, the area required for the 3 transistor dynamic cell is quite large. Okay, then as the area is large, then this limits to use this memory as a storing element, because area required is more. So how to reduce the area? So there are various approaches to reduce the area. One of the best approach is that the 1 transistor dynamic cell. 1 transistor dynamic cell, and this 1 transistor dynamic cell, it is like, or its arrangement is like as this. Okay, so there is a 1 transistor, only 1 transistor, and this is a capacitance. Okay, so by using this transistor we can store the data onto this gate capacitance. Okay, this is the capacitance, nothing but the gate capacitance or transistor capacitance we need. Okay, so therefore data will be stored onto this gate capacitance, and only one transistor is required. Only one transistor is required. This approach reduces the area and it increases the number of bits per chip. Okay, it consists of a capacitor Cm and a pass transistor. This is capacitor Cm and only one pass transistor. What is the right operation? So to do the right operation, we have to make this read line or write line. For right operation, we have to make a right operation. So for this, whatever the data onto this, that will be stored onto the capacitance when this row select line will be equal to high. So we have to make a row select line is equal to high, then whatever the data present onto this bus, that will be stored onto the capacitance. If the data stored is 1, so this will charge the capacitance, and if the data stored is 0, then it will discharge the capacitance. Okay, in this way right operation will be done. In case of right operation also, so we have to make this right operation, and in case of right operation we have to activate this transistor. If previously stored data will be equal to 1, then it will increase the voltage of this line, and if previously stored data is equal to 0, then it will ground this whatever the bus line is there. Okay, so this is simple technique there. Okay, so it will be equivalent circuit diagram of this will be like this. Okay, and to increase the capacitance, there will be a silicide will be increased here, implemented here or inserted here, so that the capacitance will be increased. Okay, so this is the stick diagram of the one transistor dynamic cell. Okay, so this will be the pass transistor, this is pass transistor. Okay, and this will be the capacitance plate will be there, this will be the plate, and on this plate the data, so on this plate the data will be stored. Okay, then what is the performance, that is what is the area, what is the dissipation, and what is the volatility. So in case of this one transistor dynamic cell in same area, that is 4 mm by 4 mm silicon chip area is there, data storage bit, it is about the 12 kilobits, number of bits are increased. So in case of previous circuit, that is 4.8 kilobits will be there, now here almost it is 3 times will be there. Okay, or it is more than double. Okay, the data will be increased here. So power dissipation with the cell, there is a no static dissipation, but static energy while reading and writing must be considered. Okay, the power dissipation is small, but we have to consider the while reading and writing what is the power dissipation. Okay, volatility, the data is in Cm. Okay, the data is stored onto this capacitance. Okay, it will be held only up to 1 millisecond or less, thus periodic refreshment must be provided. So this capacitance, so charge will be stored onto this capacitance. So this capacitance, it will have leakage current, this transistor it will have leakage current, and hence the data will be stored, that is in the form of charge, and that charge is going to be discharged by using this, by the leakage currents. Okay, and hence after some time the data will vanishes, and hence we require the replacement cycle. Okay, so that's all about today's video. We will discuss another techniques are there, that is pseudo NMOS technique, pseudo RAM will be there. So we will stop here for the today's video, and then okay, we'll stop here.